Students, this is going to be your video on forces, at least for the next little bit. All right, so the bits that you probably have questions on the homework. And this video is going to do double duty. Radford University students, this should make sense to you in the context of your homework. Governor School students, it should make sense to you too. It may not make perfect sense. You may have questions. All right, obviously the high school kids, you're going to have calculus, and the Radford kids are not going to be, you're just seeing this for the first time. So it's kind of, we're going to try to get as much as we can out of this, but, I'm kind of cramped for time, so we'll do what we can here. The biggest things that you need to know have to do with Newton's laws and in drawing your diagrams. Everything else we can deal with. So the important thing for all of you is Newton's second law, and I'm going to write it in the way you're probably going to use it, is that the acceleration looks like the sum is sigma, the sum of all the forces, which are vectors, over the mass of the object. All right, so this is your second law. All right. Now, this is the thing, right? It may be arranged in other different ways, but oftentimes what we want to do is state what the forces are on an object and use that to essentially solve a kinematics problem. So we'll do an example of that in just a minute. Actually, let's zoom in a little bit so maybe this has a little bit better. Now, this is your second law, and this is the thing. The first law is really a consequence of this. It's saying that if the sum of the forces is 0, then A is 0, which means delta V is 0 because time just keeps ticking by. It's just a clock. And so V is constant. And that's V is a vector. It means it keeps going in the same direction with the same speed. That speed might be 0, but if it's not 0, then it's uniform. Now, the third law is a little different. And there's not too many places where the third law can come up and it makes a huge amount of sense. But sometimes you need it. And what we'll do is talk about it more in the context of when we talk about momentum and collisions. But what we're talking about is objects that are interacting. So we'll label these two objects 1 and 2, and they're going to interact in some way. This might be a collision between them. This might be, gravity or electromagnetic forces. Whatever it is, if we can identify a force that, all right, we'll call that force F, but we have to label it. The standard I'm going to stick to for this video is we're going to say it's by one object on one object. So this is the force that is by object 2 on object 1. So if we have this for object 1, then object 2 will have a force that is the same length and in the opposite direction. So this will be force 1 on 2. Now, you may see different ways of labeling these. I can't remember what Radford does. I almost always say by an object on an object. But you may see it from other teachers that it's on this object by an object. But it's okay. So right. So if we have a force F and it's A comma B, the way I'm interpreting that is force by A on B. Okay. But the key sort of thing here is we can identify these equal and opposite direction forces. They're on different diagrams. Right? One is for object 1, one is for object 2. They're on different objects. They are the same size, very roughly the way I've drawn this, they're the same size, and they're in different directions. They're in exactly opposite directions. That's kind of the key thing. So that's our 3 laws. Right? That's not terrible, right? But this is the thing we're going to use the most of. This comes up when we actually have to consider 2 different objects. So we will occasionally bring that up. But a lot of the stuff I want to deal with now is just one object. And I also want to introduce this idea of the free body diagram. All right. So let's describe, say, here is a car, and here is the tree that is trying to run into, and put some happy little branches and stuff, and more tree on it. The idea is that these things are going to collide, right? So the car is going to experience a fairly big force backwards, which we'll call N for the moment. And we would write this as N by the tree on the car. And it's going to feel some other forces, right? There's going to be the earth pulling it down. So we'll have the weight, and it is by the earth on the car. And then we'll also have, maybe there's some other forces going on. We could put in the air resistance, which would be a drag force. And we are probably driving this on a road or on ground or something. So we'll put in that there is some force, which we'll call N again, because it turns out when we talk about these collisions, they're going to be the same thing. They're what's called normal forces. But it's going to be ground on car. So that's the things that we're going to have here, and maybe there's some other stuff going on. Maybe we can account for the motion of this thing by some force driving it forwards. And so engine on the car, or maybe it's the wheels on the car, something like that. The idea is that we could also put a set of forces on the tree. So I'll do the tree stuff all in red. There's a normal force by the car on the tree. There's a weight force I'm running out of space here. The ground supports it in some way. And the tree's not moving, so maybe there's nothing else holding it there. Maybe there's some other forces in here, but at the moment of the collision, this is what it's experiencing. So maybe the tree starts to move and goes that way. But the gist of it is, this is a complicated drawing. Right? So when we want to draw the actual free body diagram, we want to get rid of all of the extra stuff. A free body diagram, all it does is it takes our complicated object that we drew, say our car here, and it turns it into a single point. And so that single point we can go and put in the forces. All right, so I'm going to do this twice over here because I have something, there's a couple different ways to try to lay this out. But let's say that we have on the car, we have the weight, and what we said here, the weight of the earth on the car. We're going to simplify that. The idea is that this should be clear to you what we're trying to do. All right, so if you understand that this is the weight force caused by the earth on the car, that's good enough. And then we can put in that there's I hear knocking, so give me a moment. Okay, I paused the video. That was really weird. There was a knocking at the door and no one was there. I'm alone in the building, so I'm kind of addled. But, we'll get on with it. Okay. So there's going to be a support force by the ground on the car. So effectively you get that this is the diagram for the car. And we're going to put, at the moment of collision, there's the contact force between the car and the tree. So we'll have in tree, car, like that. And, it still has some velocity, so maybe it has a negligible force. I'm going to stack it up like this. So you get that this is everything that's going to the left. Because the idea is we're just going to add these vectors up. So this is the drag force of the air on the car, let's say. And we'll put a force off to the right. That'll be the engine on the car. And that'll be the applied force. That'll be the force that the tires are putting on the road, or maybe it's a rocket engine, and so it's the exhaust gases pushing it. We're not exactly certain what's going on here, but we're accounting for all the possible forces that act on the car. Now, you may also see it that instead of lining these up like this, all right, I'm going to cross this one out. You may see that they're just lined up like that all of them start here. Now, this is kind of the important thing, right? There's a couple of rules to doing these diagrams. You only put forces on a diagram. No velocity, no acceleration. Now, this thing, right, we're trying to draw this picture of a car. This could have been like a spaceship, and all these forces are on it, but it happened to be going upwards for some reason, instead of driving to the right. We don't care. All we care about is the forces, because the forces are going to directly tell us the acceleration. They don't tell us anything about the velocity. And we don't put the acceleration on because we don't want to get confused. Only forces. And then it's translating this sort of notation is by object A on object B. Now, the way this is shaped, we could, in principle, draw a slightly different diagram. Let's just draw a car driving. All right, so I'll draw it down here. Here's a car. It's going to drive off with some speed v that way. Maybe there's an acceleration here. We don't know. But we're just going to put in the stuff that it needs. We'll also make sure that it's a rocket engine so we can tell exactly the driving force on it. So there's a support force because this thing drives along the road. And we'll just put in, it's this what we call a normal force by the ground on the car. There's a weight force. And one of the the third thing is that we kind of want to try to draw to scale. So instead of this black line I've drawn here, I'm going to draw a green line. The weight force isn't necessarily as big as this support force. So we'll put that in. Now this thing's moving through air, so I'm going to put in a drag force. And this, what it's going to do is part of this drag force is going to make up this extra distance. So it's going to come down like this. And it's the drag force of the air on the car. And then we'll put in that the car's rocket exhaust is pushing the car forward. So we'll have a force like that. So there we go. So that's some applied force. All right. So, all right, we want to draw to scale. And now, if we have something like this, where it's at an angle, we want to find components. So we'll put this in as number 4. So that means we have to define some directions here. All right, so ignore this line I've drawn there. That's unimportant. Let's put some directions in. So in green, I'm going to come up here and say, well, we'll take up as positive, and we'll take to the right as positive x. So that means this drag force has components, and what we do is we find what those components are. So it's just dx, dy, and there's some angle involved here, theta. And so you've done components when you've done vectors. That's not anything horribly difficult. So we are going to do some problems where we'll deal with that. But it's fairly straightforward, I think. So the key sort of thing is that when you do a problem, whatever the problem is, we want to draw some sort of diagram that makes sense for it. So if you're watching this, this is where I'm going to pause the video and set up to do problems. You've seen kind of the outline of things I wanted to talk about, the 3 laws and the diagrams. And the diagrams are the important bit that you get out of this. But, you know, this is a time where if you want to take a break, it's good, because I also need to take a break and think about what I'm doing and then come back with a proper problem.